Francois, Director of the Robotics Institute. It's my great delight today to introduce Professor Francois Pomerleau from the University of Laval. I won't make a long introduction. I will note that Francois is responsible for getting me back into field robotics after a long time. He's like, you're not doing field robotics anymore, you should be embarrassed, and he forced me to come and do field robotics again, which is great. He in fact holds the Canada Research Chair in field robotics, which is great that we have one of those. I'm very, very proud that you have that. And I will say, many of you probably know that Francois was a postdoc in my lab about 10 years ago. 10 years ago. And in a way, he kind of ruined some things for me because he set the postdoc bar very, very high. So I didn't really understand what a really good postdoc could be before Francois showed up, and then after he was gone, I understood. And now the standard is hard to beat, although we have Sven, so he's up there too. And Wenda. I think that's everyone. I won't go any further, and I think you're going to tell us all about some fun stuff with snow and ice.
Yes.
Okay, leave it to you.
Thank you. Thank you everyone for being here. Today I will do a talk about autonomous driving in snow and ice. The talk will be rather high level, and just to give you a direction of the lab and where we're going. And it's sort of a motivation to convince you to do field robotics if it's not already the case for you. So why would we study autonomous driving in snow and ice? That's my international slide, so you should know Canada is over here. Well, some of my students told me that it was hard to spot if you're not used to see the map from the top. Shouldn't be a surprise that for 6 months of the year, 65% of Canada is covered by snow. And here you can see actually the 50% line extend, which is sort of, it's a different thing. We forget about it, but in Europe, this 50% line is actually way higher. So it's important for us to check what's going on if we deploy autonomous system in snow. Unfortunately, when we talk about snow, we need also to talk about climate change. So you should all know at that point that the climate is warming up. And here's two maps, one from 1985 and the other one from 2021. And the color is actually showing the quality of ice, or how old is the ice. And you can see that we're losing a lot of those 4-year plus ice. And those ice are very strong, very thick. And it's, on one side, it's causing some challenge, but it's also opening some opportunities. More and more what we're seeing is that there's new trade routes that start to open up north. And even I heard that this year there was the first Chinese cargo ship that went through the Arctic. So on one side, climate is warning. On the other side, there's an opportunity. But with, again, that opportunity comes some other problems. And here, we will have to talk eventually to the Arctic sovereignty. Because we tend to forget, but our neighbor on the north, on the other side, is still Russia. And they tend to be way more active in the Arctic circle. So here we see all of the green circles, or the NATO base, and the red one from Russia. And we see that the level of activity is actually quite different. So this is why you hear in the news, the government wants to push a bit more of activity in Arctic sovereignty up north. Which is interesting, but there's another layer. So world changed a bit. When I was doing research, we were not talking about defense that much, but now apparently we can go to war. So the extra level that is going on that, and I would argue, is that we also need, so that's the 10-minute...
Do you have enough chairs back there? There's a bunch up here in the front. Don't be shy. The derivative of the audience is not monotonically decreasing.
All right. So we were talking about Arctic sovereignty, but I would argue that we have another role to play in is technology sovereignty. that yes, we can buy very cheap robots from other countries, but at some point, if something is happening, we need to have the brain power to actually have our own robots. And hopefully, I said, it's your job eventually. This is why we are training you, is that we can actually have that technology sovereignty. So we want to study robotic in ice and snow, and then I'm telling you that there's climate change, so probably there should be less snow, so where are we going with that? Unfortunately, with climate change, there is more energy in the air. So with more energy means more extreme events also. So we have more storms, more extreme temperature to deal with. So when we need to think about future technology, we need to plan ahead that those events will come up more often, and we will have to deal with it. So anything that goes along robustness of the algorithms, how to experiment with very niche temperature even, this is why we need to investigate it. I will give you two examples of those extreme events. They are Quebec centered. So the first one was the Great Ice Storm in Quebec City. Just to give you an idea, over 6 days there was three ice rain events back to back, which triggered 10 centimeters of ice all over the infrastructure. So 10 centimeters of ice on all of the power lines, the power grid, and we had major power line that was just falling down. That triggered at least 5 million people without electricity for more than 33 days, which is way beyond the 3 days of water that you should keep at home. And unfortunately, there was up to 30-ish casualties through that time. They had to ask the military to show up, and it was a big thing. More recently, we had a flash storm very close to Montreal, 75 centimeters of snow in 3 hours. That's just what would fall, but if you put wind on it, and so snow tends to pack on one side, and you can easily have 1 to 2 meters of snow on the highway. 300 people were blocked for 8 hours. The emergency system were not equipped to move, and they were stuck also on the highway. So people had to wait essentially to get out. So those extreme vehicles some trouble when we start to talk about robotaxi, for example. We tend to have some sort of acceptability issues that are we ready to have the technology, or what will happen if all of that will it make worse? So we should work on that. Asking our question, are all the algorithms that we're developing are robust to those kind of events? This will open up to civil security. Do we have enough mobility in snow to move and to do a bit more of search and rescue activities? And clearly, working up north, there's a tendency for defense, but now we're talking a bit more of dual purpose. It's also helping the mining industry, the agriculture, the forestry industry. If you get a truck stuck in the snow or in the mud, it's the same problem for all of that industry. And in general, as anything related to automation and robotization, we are in general there to help for better productivity, which in Canada tend to be low these days. So with that in mind, this is how I created the NORLab with the mission to explore the complex relationship between robotics as a whole and adverse environment. And this is where the researcher in field robotics fit in the general mission of the lab. How do we do that? We're positioned in Quebec City. You see the dot here is Université Laval, and we have access to a research forest that is about the size of the island of Montreal. Always forget I didn't put it with GTA size, but it gives you an idea of the scale. What is very nice about that research forest is that it's a subarctic area because it's rather high. It's a humid subarctic condition, so there's 6 meters of snow falling there every year, and we have 6 months of winter, essentially. You can ski to work, and Tim is a good example. So when we invited his lab, he was actually cross-skiing to the similar place to give his talk and be very happy about it. On top of that, we are building up a large fleet of robots, and I want already to thank all of the lab, because this is essentially a presentation of their work. But our main system is the ClearPath water robot that is up there, fully rugged for rain, snow, and all of the harsh conditions. And lately, we have a mobile lab, which is the size of a tiny house. Behind is the garage with all of the tools, and we have the command center in front to deliberate. We are autonomous in terms of electricity, so we can at least deal with one charge. Fully heated, was built in Quebec, can sustain 1 meter of snow on the roof, so we don't care about deploying in winter. And that's about the size of the lab. I think we are 20-ish right now. I want to point out we are 2 profs, so it's a joint collaboration in there. Our 3 research trusts are navigation in snow and ice with those 2 projects. That will be the focus of that talk. We have a full trust on forestry with AI, and we tend to be very active in the search and rescue and defense area. But as I say, today we'll only focus on, could be similar on each of those tracks, but we'll focus on snow and ice today. Still, I really want to highlight the nice work of the other professor, Philippe Giga, that is within the lab. That's a very short overview of what he's doing, but we're trying to automatize the whole line or the process for forestry, which goes up to cutting. This is the messy area. They tend to do that during winter. You will have debris all over the place. They are banging with the tools in front, so it's very hard for perception problems. And lately, what was published is that they are more into those segmentation image, and they are going up to the species identification for trees. And the idea is to go to precise forestry. So instead of cutting everything, the operator should know the value of each trees and cut only the one that makes sense. In a perfect world, that would be triggered up to the mill, and they know actually they have the capacity to process it. So this is why it makes sense. Here we have an example of species identification. Here they are actually identifying the cutting point, the size, and the angle of the trees. And down there, so here we are finding trees that are up. Here we are on the log that are on the ground. And once we can identify, so that's the second stage of cutting. So that one will do a messy pile, the other with the arm, which is good because it starts to look like a robotic arm also for the bin picking activities. We'll pick the log and do a very nice pile on the forestry road there. So by being able to identify the log with FP Innovation, which is the entity responsible for R&D in the forestry in Canada through Canada, they could show some basic automation of picking the log. The other trust that I just want to tease a bit, our lab was part of the DARPA Sub-T Challenge. Those are the large challenge that run since 20 years. We were the first Canadian teams to qualify, and we won also a couple of prizes there. Our specialty is 3D mapping and localization. And here's the example of the final round of the competition. That triggered also some activity for the IDEAS program with the Canadian Defense, where we had to look for some radioactivity sources in different harsh conditions. So those are the 2 trusts that I will not speak about too much, but today we'll focus on the snow and aquatic project. The lab started in 2017, so we had 2 large NSERC Alliance grants. And we are starting the Robotics project, and this is a bit why all of the lab is around here. So for the people in the audience, people from the lab can raise their hand. So yeah, I brought a lot of my lab around, so we can tour a bit the facilities at UTIS and at the Institute, but we were also at General Dynamics Lens System yesterday to do some tasks. So those are the 2 major programs. And today I will just give you some quick example of publication within 2024 and 25. For deeper discussion, they are all there, the first authors, so don't hesitate to chat with them. So when we talk about robotics in ice and snow, actually we should talk about the cryosphere. So the cryosphere is the area on the Earth where you can find water at its solid state. I was invited to write an encyclopedia article about it, which is nice just to get an overview. But here's essentially all of the places on Earth where you can find solid water. And once we do a quick review about what people were doing, there was a lot of the early field robotics that was deployed in the Antarctic, mostly sponsored by defense area. And those robots were gigantic to deploy, but they started the process. Some of the good things to highlight. So here we have Tim's lab that was deploying on permafrost on Devon Island up north. It's in the Arctic Circle, right? In 2009, and it's probably where it faded down the field robotics, and now it's back again. That's why. Yeah, and I'm happy about that. And today I will show you a couple of examples of our vortex deployment, mostly on frozen ground and snow cover area, but we'll have also one on the glacier. So I split the publication into three parts: perception, traversability, and motion. It's not all of the labs that actually cover the whole pipeline of robotics. As far as I could tell, most of the lab are on perception because it's easy. You don't need to go outside and to have motor in the loop to deploy. You will find a bit more on traversability and path planning, and it's then either they only focus on motion and control, or then you have the field robotic people with you have to actually understand what's going on at the tree stage. So we'll start with the perception. We did some early random work where the price of lidars went down essentially in the recent years. When I started, it was the Velodyne 128 beam that was big like that. I'm not sure what was the weight, but I was walking like that when I was carrying it. It cost 120 Swiss franc, so a lot of Canadian dollars. And it was very expensive, and very few labs were able to get their hands on. But nowadays, we can have a LiDAR that costs 1,000 something, which trigger in my head that we can actually throw them down staircase and see what happens. And this is how we trigger one of the research, where we put an IMU and the LiDAR in some sort of protecting cage, and we realized that the IMU was saturating at a lower rate than expected. So what you see here on the graph, as the cube is tumbling down, you see that the blue line sort of cut off, and this is where, when it hit the ground, starts spinning, we were saturating. So we did some math behind to recover that angle quite well, which triggers some interesting discussion that bring us to a glacier. So we were actually happy to set up again, now we call it the sphere because we're all very original with our names. We still have the same LiDAR and IMU, and we were asked by NASA GPL to investigate some interesting questions. So we were part of the I always forget that, Exobiology Extend Life Surveyor, so the ILS project, where they had in mind in 50 years, so don't be overhyped about what's going on in those images, to build a snake-like robot that will go down one of the moons of Saturn to eventually search for life in one of those crevices. So that's their plan, and we'll start with that. But where they were concerned is what happened if the snake actually lose traction and drop down in the crevice. Will the mission stop, or would they be able to have a localization system that would recover? So that sort of started some interesting research question where I asked the student I want the system to mechanically break before our software lose localization, essentially. So we should be very harsh on the system and see what happens. Here, what we were doing as some demos, essentially we're trying to map just by throwing down the system. So here's a simple crevasse and here's a moulin. A moulin is an interesting thing that happened on the glaciers, that the water will melt eventually and the water need to evacuate somewhere. So that will sort of generate a hole, and it's super dangerous to go down these moulins because there is a river that will flow at the bottom. So even for the people studying glacier, those are interesting to see, to have an early map to trigger whether they should go down or not. So here's one of the system that essentially take 30 seconds or 5 seconds, and those are the kind of reconstruction we could bring up with these. Here you see on the left side the moulins that was literally mapped by throwing down the lidar, and here's the sort of 20 seconds trajectory going down the crevasse. So that was interesting. There was a lot of safety issue to be on the glacier, so we were 3 and we were assigned 1 safety for all of our to walk around and to do our recording. And what we discovered afterward is that that guy was Christian Steiner, and he's an official national geographic explorer. And his side job was to escort us on the glacier, and he was looking at what we were doing. And his job essentially discovered the only active volcano in Canada, and he had to went down with the full equipment because of the toxic gas. And what he told us is that essentially they need a piece of paper and they just draw where they are, and eventually they will arrive to a place where they need to decide, should we put the harness and go down, or we let it go and we move on. And this is, it's a risk management thing. So he was very enthusiastic in having something that he could throw and then take an assessment quickly if there is another room or something else that makes sense, that worth the risk of going down. So that's our future work on that, but it was actually very nice to go in the field for a reason and actually trigger another research question with someone else. So that's a good outcome of doing field robotics. A bit before, this is Pomerleau, this is where we do most of our experiment. We show up the first 20 kilometers of autonomous driving in a remote forest. We set up the goal to connect the garage to a remote cabin where there was no electricity or nothing, and bring some goods there for the full week. And during that whole week, everything happened. We were close to spring, so we were oscillating around 0. So we had rain, snowstorm, high wind, during days and nights. The whole idea here was not really to demonstrate a new algorithm, was just to be out there and see and list all of the problems that would trigger to be in that kind of environment. So the paper that came out of that is to make the distinction between a forestry road, which is rather wide, to a forestry trail, which triggered way more problem because the path is very narrow. We could study the influence of weather, so all of the colors you probably cannot read, but that's not important. Any color change there, it's a type of weather that happened during our deployment. We could do study on the number of GNSS satellites that we needed, and on the stability of our lidar pipeline in the forest, and also explain the concept that in urban environment, you have the idea of the urban corridor or urban canyon that triggers some problem, but in the forest, actually, we don't see much more beyond the 2 tree lines. So we are essentially always in a long hallway. So that essentially the lighter color is where we have more uncertainty in the driving direction. Out of that, so now we are talking about building a map for localization of 1.5 kilometers. And of course, there will be some drift that will be triggered out of it. We could have another paper that was using the gravity from the INU as a constraint to stabilize the map. So here's just the quick before and after. Here you can actually appreciate what kind of environment that we are dealing with. So the garage will be here. There's a couple of buildings here. The teams, when we spend the week, sleep over there. And that's one of the forestry track that is there. And again, that early discussion triggered the fact that we're drifting on Z often on our large map. And combine that with the deployment on the glacier, where for the first time we had the pressure sensor just to see what we would get out of it. Produce yet another idea or another paper. So here's a robot inside. You will take the elevator, and we can localize in the elevator, go out, and we'll do all the way on the other side, and we'll close the loop. This is not usual to be in an elevator. There is no actual features to allow you to localize. So what is going on in there is that we have pressure sensors that help us. And if I start from the aerospace era, pressure sensor were within 100 meters of precision, was good enough to not have two airplanes collide. And if you go down the years with the drones, now they were at 10 centimeters, and if we look at the literature for the maybe 2020, they were going down at the precision of 5 centimeters, and with that paper, we were at 8 millimeter precision. And all of what you see there is our ICP pipeline, and we swap the Z correction only for the altitude out of the pressure sensor. And I will just point out a tiny detail. There's a very small ramp here that we pick up perfectly, even with that. And the trick we had for that, if you're aware with GPS or GNSS, the navigation with satellite, if you want to get way more precise, we use the GNSS, so we have a fixed antenna that with broadcast correction to your mobile system. So we use the same trick with the pressure sensor. We have a fixed pressure sensor and then a mobile one, and the fixed one will pick up the variability in the environment and will transmit the correction to the mobile one. So this is where we are at. And the future work was presenting this morning. We'll try to pick up the gravity vector out of an array of pressure sensor so we can support even more tumbling lidar in staircase. Another set of publication that went out of our deployment is I talk a lot about lidar localization, but there's also camera-based localization. And when we walk in the forest, or we try to use the auto exposure, or just any exposure, we have a high dynamic range problem, especially in snow environment. Here you see an example that eventually, if you want to have the texture in the snow, you will saturate in the dark, so the trees are getting too dark. If you want to have texture in the trees, you will saturate in the white. What is happening is that snow is highly reflective, so if it's a sunny day, you will get out of the dynamic range of your sensor. And here's a general example, just a small loop, where the auto exposure of the camera will vary from 1.5 milliseconds up to 10. If it's going too low, we'll start to have motion blur problems. And all of that triggers that the student was not able to fix one exposure time to make sure to minimize everything. So he went down the rabbit hole of saying, okay, we'll investigate which of the auto exposure algorithm is better, to realize that to test that, you need to have the camera outside in the loop, because it's a control loop, and it's very difficult to compare. We are very good at doing dataset, so he proposed a rather large dataset where you build an array of cameras that would actually shuffle through all of the exposures. And here we see a couple of examples of those areas where we gather that. He also did the emulation code, so you can run offline any auto exposure algorithm, and that would generate the proper image to the given exposure time. And funnily enough, or no, he tested all of the auto exposure that are there up to deep learning algorithm. And unfortunately, the conclusion is that they are all as good as the one by default in the camera. So at least now we know, but before it was super hard to know that. So now our future work in that is to actually, now that we're a proper benchmark that cover all of the solutions, to actually propose a good solution to that. Moving to the traversability section. By the way, that happened to us when we were doing a teach and repeat, teaching the path during winter, and then they decided to repeat it during spring, which actually the localization worked perfectly fine, to realize that we tend to have a part of the path that is on frozen ground, and then they just lost the robot and it took them 2 hours to get it out. So traversability is the more generic term than obstacle avoidance. So avoiding a wall is rather clear, but the quality of the ground could also stop you from going to from one point to the other one. So traversability is the generic term of that. It turned out that detecting trees and rocks is the easiest part. Detecting what's going on in the ground in front of you, that is super hard, at least for us. One of the ideas that came out is to use the camera to predict the quality of the ground in front. When looking at the literature, we realized that having a camera mounted on the UGV is actually very good to see what's going on in front. But if you think about it, you try to project on a plane that is going further and further away. So we start to generate those artifacts that get very sensitive to motion blur and anything about it. So when you start to have a segmentation algorithm that try to predict the quality of the ground, eventually we're not going that fast, maybe 1 or 2 meters per second. We need at least 10 meters to understand what's going on, and we're having very bad results. The proposition of Jean-Michel was to actually use a drone that would fly in front of the UGV, and that would be able to keep the proper projection for the ground inspection. So here's the full proposal. So can drone actually help for off-road navigation? Here we have some sort of extreme example, which is there's a bush, and it happened that there was a concrete block well hidden behind that would never be able to be picked by the camera. The good thing with that is that we can train a learning algorithm by flying in front of the robot, so we know in the future that the robot will cross that tiles, and we can start learning what the robot is experiencing on a given patch of image, which eventually lead to the idea that you can scout with your drone and survey. And here it was just an example of trying to predict the Z variation, the vibration in Z that would be picked by the accelerometer of the robot. So there was some offline training, and here at the deployment, the drone would scan around, and here that would be the path that the general path planning algorithm would take, minimizing the variation on now that we are there, the future direction for that was done with the DJI drone, so off the shelf. We realized that we need a tighter communication between the UGV and the drone. So Jean-Michel started to build his own drone. We have some idea of having a tether with the UGV, so the power is not an issue anymore. So there's tons of opportunities that goes with that direction. So that was image-based, but the actual quality of the ground is way more complicated or complex than what we can actually see. Here's a general example of how messy it can be in the forêt. So within only one picture, we have actually a lot of mud, ice, rocks, deep snow, shallow snow, and the whole idea is that it's good if you can predict what's going on, but if you have 1 millimeter of snow, everything looks like white and would be badly segmented, and you have no idea what's going on under. And also that makes us think that we don't know what is snow. Snow can be anything, can be a crust of ice with some powder under that will lose traction. So it's quite a complex material, and it's visually hard to identify. So we went into the direction of using proprioceptive information, so to use the batteries and the current to trigger on the information. And clearly for the any learning algorithm, we were lacking a lot of data to be able to do that. So we hand annotated a couple of them and tried to go online to gather other data sets and trigger on the problem that labeling terrain is probably not a good idea. It's a continuous spectrum and trying to actually segment that this is tile, this is grass, and this is dirt is more tedious than expected. Our clustering, so we could show that the clustering was working well, but it was very hard to generalize. So every time we're adding a new platform that would have the data gathering inside, the network would trigger in first identifying the robot, and then on what type of ground that robot was driving. So it was sort of going over what we wanted. So we are still in that area that clustering or labeling terrain is hard. So we decided to go more into the, let's say, the motion or the continuous aspect of it, and with the intention to say, okay, then if it doesn't make sense to know if it's grass or dirt, let's see on the control point of view if we can measure slip, and that would be how we define the ground. So again, we were going to the literature to see if terrain can highly influence motion prediction. Again, going after good data set or something that we could start to build on to realize that most of the people providing their data, if your robot can actually move forward or turn, so that would be your control space that you want to explore, all of the data was forward and a bit turning, because that's what humans do when you have a robot. You go forward and you turn a tiny bit. So it was very hard to get through that. So we went through with an actual protocol to gather proper space exploration for control that would record the interaction of the vehicle, a given vehicle, up to the ground. And here, using the ideal model, this is the kind of trajectory, so that would be the ego motion. So we have a skid steer robot, so we can turn on spot, and we would trigger those trajectory randomly. So that's what the robot thing is doing. And since we have a good localization pipeline for the whole system, that is actually what is going on with the system. Here's the same information, but that's the global point of view. So our protocol, we define an area, and then a safety area, and then we let the robot explore the space and do those curls. And again, that's what actually is happening. But once we have that information, actually we have all of the slip information, and we can dig into that rather deeply. Funny thing, it's not easy on the robot. I don't show here the concrete where the tire can bend up to 30 degrees when it's turning on spot. But this is the kind of overview of what we did for different conditions. Most of the controllers we're dealing with are kinematic based, so they deal with velocity, and we have at least one data set where everything goes out of whack, which is here. So we're more into force, and that is a very interesting data set to dig into. Out of that, we wanted to build a metric that would combine the rotation uncertainty and the linear velocity, and connecting that to the inertial metrics and kinematic energy, we come up with the unpredictability metric. So here would be our warthog. That's your control space. So here's the angular velocity, so how much you want to turn. And here's the linear velocity. So if you're here, you're moving forward at 4 meters per second. And here you're turning at 4 radians per second. And those are the boundaries, that's our safety on our robots. And what we could come up is that, yes, if you know that there is slip, actually you can put that in your controller and you can offset that. That would be a bias. But at some point there's an area where you have no idea what's going on, and it's getting more random than anything. So it's rather bad to have a controller that stays in the purple area, essentially. So we have a metric going from 0 to 1. 1 would be I have no idea, I'm sending command and the result is random. 0 is that I'm sending command and I'm doing exactly what I was planning to do. And what we see on ice is, of course, when we start spinning, we have no idea with the general velocity controller what is going on. But we tend to have two good spots where the Vortex actually have good traction on the ice at 1-ish, 1.5 meter per second. And the same thing for asphalt is that this is typically what a human would interact with the robot. Is going forward at 1.5 meter per second, which is sort of the sweet spot of the system. For the asphalt, we struggle a lot at low speed, and same thing on the side. And at low speed, what is going on is that the asphalt has so much friction that the robot will act as a torsion spring. So you put a bit, and then if you release the rod will not move but will turn, and then you release the control, it will come back exactly at the same place. So when you try to aim into a tiny doorway, us human, we will do that until we pick the friction coefficient, so it's not, and then you move a bit and then you let it go again. So this is where we tend to have some sort of problem, and that trigger another research topic of dealing with at least the Warthog as a torsion spring at low speed. Some of the ongoing challenges. This is our campus during winter. That's me going to work. It's not always like that, but it's not surprising that it looks like that. It's super hard for us to deploy during those times. This is William, took the bullet and went out to record some data. And I want to share with you two new data gathering of snow dust, which is actually super hard to record, and even the lab discovered them yesterday when I was presenting them to our industrial partner. Here's two different lidars. They are both 128 beams. The frequency at which they work are different, and I will attract your attention on the corner there. It will loop again. And then that's snow gust even that is coming up. And on the messy part, so that one has a larger field of view. All of the red that you see going through is the snow that is moving around. There's, even during a snowstorm, there was not a lot of those even. So here's us in the sort of the corridor. You will see a quick snow gust passing through, and here we see the messy part of the scan. And finally, another one, the wind is sort of blowing into that direction, and you will see a full wall, like a wave going through. And the problem with that, the snow, not too bad. We can filter out, it's like a black and white noise, and we get through it. When we have coherent particles going through our localization system, it can be attacked very well, and here's an example where our basic localization pipeline will lose 45 degrees and jump 2 meters ahead, and it's just because we have this coherent particle drift in the same direction. So that is annoying. We were lucky to do some deployment with the explosive experts. We did the teach and repeat, so that's the red line there. Let it go, and ask the guy throw as much smoke grenade that you can until the system breaks. And we were only running on LiDAR. I was explaining to the stakeholder that it's okay to fail. We are here to make it happen. It's actually, I want to see if there is a point of having a radar. And for the first time, we could record all of that. So here's what will happen. The short story is that it didn't fail, and I was sad. But I could gather key point or key element where it was interesting. You will see the front camera, the path, our local scan in the LiDAR. This is what we're using for localization, and this is the radar feature extraction. The hollow in the middle would be the robot. It goes super fast, so I will pause it right after, but at least that you can see what's going on. If you're not sure, watch the camera, but essentially we're going through one of the smoke grenades that was bouncing just in front of the robot. So if I pause at the exact frame where we have some concern, we see the smoke is covering all of that part. There was an actual truck, military truck that was parked there, so it's a bit concerning that we can lose like those massive assets in the field of view. There was also a person right behind, and actually the radar can pick it up. Hard to identify, but still can track it. And there's just one frame. That's the worst of and this is why we could still localize that we have those two walls that would show up. But it was at 10 Hertz, one frame, where most of it was occluded. And yes, if we could trigger to change with the radar, that would still help. So fusion will help here, but actually making it break didn't happen. So I'm a bit still in between with the radar. In terms of control, this is the thing that we're dealing with all the time. Here the robot was actually on the snow, and then the controller decided to get some gain because the error was too large, and the robot did in 1 second, and then got stuck there. And here's one of the cases where, if you recall the other graph where turning a bit was an issue of unpredictability, it's because the system is losing traction. So if both tracks are moving together, we're moving, but here we're trying to turn as a slight arc, and then that means that you only turn one of the tracks, and we don't have enough traction to move actually around. In terms of mobility, now we'll have a new platform that will look like a snowmobile, and what we realized that changing the center of mass of us, this is essentially how snowmobile drivers deal with. The steering wheel works nothing in deep snow. You can be like that and go forward, and it will not change. It's actually how much you change your center of mass, and you will terraform the terrain to actually be able to turn. So I put the bar very high to one master student, and we need to do that soon-ish. Here's my quick conclusion out of that. When we are dealing with robotics, especially outdoor, it's very costly to get data. And every time that we start saying, okay, we'll take a data set that exists and start with that, we finish by recording it ourselves. So here's the general recipe that I'm pushing forward in the lab. So every time we buy a new platform, a new robot, I really want the lab to actually just take it and drive around in the campus, get it stuck, do anything you have to do with it. It's on campus, it's controlled. Now you will know the boundary of what the system can actually do and not go beyond, especially when we do demos with the stakeholders. Once we are actually able to just walk behind and drive it, we can actually start an early data collection. This is what happened with our full year data set. And then you start to have enough data for sample models. And models, I know that they are not trendy, but they are simple enough to understand what's going on. And the idea is to start from that and build up for the more complex algorithm. If you do that one loop, you went on site, you did some validation, and usually, even at that early stage, we trigger tons of challenges and we start publishing right away at a very simple autonomy layer. Once we have that, we have enough data, enough knowledge on the system, we can go to adaptive models, try to support the driver. So assisted driver, we start to gain time in deploying because we know a bit more the system. Once we have that, we actually push to a larger data collection and moving. And this is where, so I know that some labs are pushing and jump to the machine learning wagon starting, but I think you need sort of knowledge about what's going on behind to understand what is your model doing. And this is, for me, where you can start to talk about machine learning, autonomous driving, data collection, and augmentation. And that's okay, but at least for me, it's the good sequence of dealing with a complex system. And finally, all of that part, it's going outside, it's the fun stuff. It's still robotics, and you need that if you want to have more data to validate your algorithm and so on. So if you don't do it, just respect the people that gather the data, because they are actually costly and quite time intensive to record. On that, all of our code is on GitHub. We have a YouTube channel. We're active on LinkedIn. We have a well-maintained website now. So if you have any questions, I can take them offline or now. But while answering, I will put that very complex slides. So you have time to process it while I'm answering the questions. But it's our latest work. We are on pre-release. We have a full year of data collection in Pomerleau covering seasonal change. We went crazy into the sensor and calibration. You even have audio data left and right on the mother. So yeah, don't hesitate to give it a look there. We are a good place to take comments on that very large release. And it's actually a collaboration with Tim's lab. Thank you. Hey. I will start with John. What's your question?
Yes. First of all, how are you getting gravity back from multiple pressure sensors?
Sorry?
Gravity. So you're going to sense the gravity.
Yes.
You said gravity from multiple pressure sensors.
Yes.
Can you talk a little bit more about how you do that?
So gravity essentially measure pressure, which means measure altitude. So you can convert pressure to altitude.
Yeah, okay.
And it's linear. It's a very simple equation. So now we start to have a sensor that measures height. It's not super precise in absolute height, but it starts to get precise in differential height. So you can use one pressure sensor as your origin, and you compute the delta with another pressure sensor that will be on top. We do the math. Eventually, you think you need 3, but we need 4 sensors to actually recover the gravity, but think that you have your basis axis, and the 4th one just for sign issue. We had to talk about it this morning, but just trust me, you need 4 sensors. Once you have 4 sensors, just by the difference of height, you can recompose where is the gravity, because pressure change with respect to gravity. And if we can pull that off, we have a lot of issues where most of the SLAM algorithm, there is IMU, MacWhip filter, which is extract the gravity vector, and then all of the pre-integration and all of the constraint that goes on. But everyone assumed that the MacWhip filter, so the gravity extraction out of the IMU, is always right. And in all of our experiments, if you start to be off-road, it's it's very bad. So if we can extract ourselves from the IMU, we can pick the direction, then we can remove it properly and then do the proper acceleration. So that would be great. And the other thing with the throwing ball is that an IMU doesn't detect gravity when there's no force on it. And then you have the state that goes all over the place. If we are independent of that because of the pressure, we are golden for actually quite some good push on that. Yes, Lily?
Just to follow on that, how sensitive is that? Like how much distance can you?
Yeah, I get the direction. So you can have expensive pressure sensors that are ceramic based. Those are immune to temperature drift, but are very noisy and very expensive. They are in the 600 range.
1,200.
Oops, okay, 2,000. And we use those as the early stage as reference, but you can buy MEMS, so very small pressure sensors that cost $6.
Yep.
They are more precise, but drift with temperature. And that was very annoying until we went into a full calibration mode with the ceramic one. William is leading that project. He put the rig in the fridge, in the freezer, heating it with a heat gun. So it was exciting, a full range of, I think, 4 degrees to plus 30. And now we actually could shrink down the calibration on temperature very small. And with the differential measurement, we are within 8 millimeters. Yeah, and that was new for us. I didn't believe that we could go that accurate with the pressure sensor, but once we have that, we sit on an extra sensor that is not used a lot in the community, and that would stabilize our long drift outside. So temperature was an issue, and then we have the general weather. So the weather will change the pressure, so this is all the forecast that there will be rain. You will have a up front or lower front that will go through. So the whole atmospheric condition will shift, but this is why we have a static base antenna. So that antenna will cap all of the big wave of the environment, and we ship the correction to the mobile platform.
Accounting for temperature shift as you're doing your assessment, like your analysis?
Well, so we do temperature calibration prior to the stuff to putting it on the platform. So we have a separate rig where they're just all on the same height, and we do this for the temperature calibration. Then we derive a model from the data we get, and we use this model to estimate the altitude afterwards. So we have raw pressure measurements and raw temperature measurements from our MEMS sensors, from which we use a polynomial to actually get a measurement at the end. And then we use 2 different sensors, one that is static and is considered 0 altitude, and then the one on the platform, and that's how we do the differential altitude, which is actually kind of like differential GNSS, where we actually have corrections for all the atmospheric conditions that would affect the same zone similarly.
So, of course, if you go like few kilometers away, then you will be different, but yeah.
We haven't checked for
We're not there yet. We're at the toy testing. Yeah, that was a follow-up.
Related, if this accurate, especially the initial pressure part, can we use them to predict linear velocity, like airspeed sensors of aircrafts, which rely on pressure to gauge velocities? Would that be something that's possible with these precise differential measurements?
So when you go to aircraft territories, we didn't try a lot of things there. So the idea would be to get the flow.
The speed, yeah, airflow speed related to your static airspeed, and then get a linear velocities out of it.
Or that you would get a static wind sensor and then transfer that to your, probably would also help. Because at least you can remove the external force out of it. Yeah, would be to investigate, but I think the whole idea of having a static something that transfer correction is good in general. It's just more infrastructure to set up. But we are doing it most of the time with GNSS, so why not having more sensor in that base? Yeah. How we go there?
Wait, so since you brought up wind, how do you place it on the robot so that how fast does the robot have to go for the air movement to cause the pressure difference? And then how do you place it?
So we had the mechanical engineering build the 3D fins on it so that it acts as a low pass filter on the small event that would be triggered by the wind. So we have a box with like a layer of a maze so that we cap actually the average pressure, and we try to filter mechanically the high frequency that will be caused by the motion. And again, we are not at aircraft speed. We are in a range where our own wind is manageable. Yeah.
I guess really quick. Sorry, we're dwelling on this pressure thing, but this is very, very cool. Do you actually need a base station static pressure sensor, or because barometric pressure varies relatively slowly, speaking, like not on the order of like multiple times per second? I don't know. Does the DGPS correction include barometric pressure data for a nearby station? I'm just wondering if you could actually just grab it, like an over-the-air GPS signal and not even need your static base.
It's under investigation. I didn't talk about it, but this dataset, for example, since we're on a research forest, we have a full meteorological station that streams at 1 minute. And eventually we have a pressure sensor also, so William will investigate if we could use actually what's going on with the base. We tried that with the airport meteo station before I bought the 2000 thing. And actually we checked what was the spec that they had at the airport, and we bought the same one. The problem is that they were streaming at 1 measurement per hour, which is, yes, it's slow, but not that slow actually. So we're not able to pick it up. And to have a base, we were not sure, for example, if the elevator would put some different pressure, which was negligible at the end. We're not sure if going from inside to outside, if we would see a gap, was negligible at the end, oddly. It seems that our buildings are not that tight, or at least ours. So we had to investigate that, so this is why we went into, we need to own the data and have that static end data. Second question was what?
One very quick last, so maybe not a scope, but I didn't realize that we're not being steered effectively, right? The tracks.
Yeah.
So it never even occurred to you have that issue with slippage, right? Where in the front, because it doesn't want to turn.
Yeah.
Is there a straightforward way to get out of that situation? Like, can you wiggle the wheels in the tracks on the static side to perturb the system to try and, I don't know what kind of control you use, but I'm just wondering if there's
A bad one, but yeah, go on. All good ideas. I have a PhD student that is on entrapment. So he's only doing entrapment detection and prediction because of all of that. So he's trying to see if we get into a singularity in the control metrics. And what we figure out is that if they all converge to 0, it's a non-problem. You're stuck. You can, anything you do will do nothing. But as long as you have 1 degree of freedom that still exists, you can like work on that one to excite the other one. So it's a mix of control and singularity detection and so on and so forth. He's ready to shovel the robot a lot, he told me. He's training hard now because this winter is shoveling. But yeah, entrapment is an issue. We have many directions. It's not, for me, anything that looked like a problem is actually a trend to research. So I'm super happy to show all of that. Yeah. Yes.
Slightly tangential. What else goes on in a research force? Like what other? You don't hear that much about research.
Yeah.
Like what else is in there?
So right now we are their main client, which is confusing them because historically for the last 50 years we have a forestry department. Where they actually, this is why it's not a place to watch birds. There's actually heavy machinery that is going through. They do some sort of study where they cut clean a parcel, they cut but let the branches, for example, in another one, and then they cut but let the top, the branch, and just take the trunk, and they let it regrow for 20 years. And then they look which one is regrowing the best. There is a ton of research. There is a pristine lake studied by Environment Canada where they check climate change trends. So it's mostly a lot of like those 50 years research long term. But the core was they looked a lot at CO2 capture in the ground. And then now, if the climate is rising, actually they are scared that whatever CO2 is in the ground gets released, because that budget is way more than if the forest burned, for example. So there's some study there. People are studying in biology moose what happens if the moves eat one branch and then the trunk need to grow like that, which means that the wood is less worth it for the forestry company. I attend weird talks, let's put it that way. So they were used to biologists, to people in forestry, in that kind of environment. And now they had to do safety training for computer science, engineering, and they were so confused because all of the staff in the lab need to do actually off-road snowmobile training, because you cannot, it's not easy to actually drive into that, but it was off of the typical crowd of technical staff showing up there. In the lab now we have a dedicated sequence. We go 4 times, 1 full week where people sleep on site. We have a cook that takes care of the food, or we have the food arranged. And it's great for the team build-up of the lab actually. And since we do that, so that 1 week we do that 4 times during winter, we are sort of the main showcase. When there's a demo, it's our robots now that is showing there. Out of the lab, didn't talk about it, but a couple of startups, and one of them is into robotic and forestry also. So this is bringing back to the big machine. So we try to reconnect with automation. It was, yeah.
Yeah, so a lot of really cool stuff. I like the warthog drifting on the hockey rink. I said I like the warthog drifting on the hockey rink.
Yeah.
So
the full video actually, the warthog go in the wall, and you see, you sort of see at the TV how much it can bend, but when you have a half-a-ton robot that go in, you see the whole wave going. But yeah.
Yeah. So for that, we're measuring the unpredictability in the control, right? The angular and the twist. How are you measuring, I guess, the disparity between the linear and the angular velocity commands versus the ones that actually experience it?
So we use our ICP pipeline. We localize the system all the time with our lidar-based localization system. And then we check at the command and we put the ideal diff drive model there, and we compute the offset between the ideal model, that would be the model without friction or any loss in the system, and our ICP based localization.
I see, so it's purely ICP.
Yeah, but the method, it's generic. We have RTS, for example. We could swap the localization by an external robotic total station. If we are in a mood of having good GNSS coverage, we could use that. The idea is that you have a localization, an external localization that localizes the body, and then you can measure wheel velocity, commanded wheel velocity, and we'll try to bring that back into the body and measure the offset of what happened. And that's the idea is to collect core low-level data. And what we realized that we cannot split the robot to the ground. So it's clearly is the sum of the interaction of the robot, whether we are on track, on wheels, and so on, the suspension and everything, up to the deformation of the ground. And the whole idea is that when we are building the software so that it's easy to deploy, but then we'll ask the community to deploy that on their robots, on their ground, and we'll try to gather like an atlas, a catalog of those slip models. And eventually the early stage is just that you can do a couple of comments and then you truly say, okay, we are close to that model, I can start driving. And then you can move to another of the model. So that's without doing too much learning out of it, that's where we'll start after. But there's a lot of effort right now in building the software to do geofence the area first, and then let the system spin in the geofence area, validate the data, and then package that in a large motion data.
Thank you.
Yes?
Thank you so much for the awesome presentation. I have a quick question about the traversability or terrain characteristically. Maybe I missed this in the presentation, but could you further explain the clustering diagram?
Yeah.
Where you what are the axes represented? represent terrain characteristics. Oh yeah, this one.
Is that one? Getting a bit more into learning than what I'm comfortable to do, clearly more on the field development. I know that this is a TSNE analysis of clustering, which it's a projection of in your space of clustering that tried to spread it the most. It was rather random every time we were running it, and the best scenario would be those where you can see actually very separate clustering. So here's all of the data related to flooring. There's some sense that snow is close because floor was also slippery, and if we go in that direction, that would be what happened to a former field when you, well, essentially so soft dirt. That would be a dirt road. So essentially that section makes sense, they are well clustered. Here, that's sort of another story. So the projection didn't work well, we have ice that is spread, and again, could justify in our head that flooring is slippery and ice is slippery, but your explanation is as good as mine. And then here we have concrete, which doesn't make a lot of sense, and at least asphalt is close to concrete. And again, this comes to concrete was the data set we found online in Italy, and we labeled it as asphalt, and then we realized that for mechanical people, there's a huge difference between them, but I suspect that from the robot point of view, it's the same. So for me, I wouldn't spend too much time trying to explain what's going on there, because at the end we decided to stop labeling the terrains. What we know from the work of the Drive dataset is that we thought there was not a lot of difference in terms of slip from grass and dirt. From the point of view of the robot, since it's a large robot, it was the same kind of terrain. So there was way less similarity or difference than what we expect. Visually, it's totally different, but from the robot point of view, they were always very similar.
Let's thank Francois again for a great talk.